let's understand partial reflection and total reflection. We just saw that whenever the light ray travels from a rarer medium to denser medium, it bends. Does 100% of the light or the complete light bend or complete line pass the other side? No. Some of the light comes back as reflection. So for example, if I say a proportion of 100, if the 100% of the light was incident, then depending upon the characteristics of the surface, there will be some amount which will reflect back and there will be major amount which will refract and pass on to the other side. So maybe 80% passed, the 20% got reflected. Okay, if the reflective surface is harder, the transparency is less, then maybe 60% gets reflected and refracted and 40% gets reflected. If it is highly transparent, then 90% will get out, 10% will get reflected. 98% may go out, 2% may get reflected. Okay, so depending upon the nature of the surfaces and the mediums involved, the percentage of the light going out and the percentage of the light getting reflecting back are different. Okay, so what is meant by partial reflection and total reflection? Let's see. Let's see, what do you mean by partial reflection and total internal reflection? So, in the first case here, there is a light source which is inside a denser medium, let's say water. Supposing the denser medium is water and the rarer medium is air. Now, you have got a light source in the denser medium. The light which is vertical goes out and also reflects vertically down. Right? Because it is vertical, it is 90 degrees, so there is no refraction. It is moving up and moving down along the same line. When the light ray gets inclined, then there is going to be refraction. So there is going to be a bending of light because the medium is getting changed. So there is refraction. The light bends. Now, according to Snell's law, sin I upon sin R should be a constant, right? So if you go on increasing the value of I, the value of R should also increase so that the ratio is constant, right? That is why if you see here, when the I is increased, the R also increases. Go on increasing the I, R will continue to increase. At one point of time, the value of I becomes such that it increases to a level that the refraction happens almost 90 degree to the normal. So this is the normal, the refraction is almost 90 degree to the normal. You have reached that stage. So that angle of incidence, the angle of incidence at that stage will be called the critical angle of incidence. It's called the critical angle, right? So what is the critical angle? It is the angle of incidence at which the refraction is 90 degree to the normal. That's called critical angle of incidence. Now, what happens when you go beyond the critical angle? So now my angle of incidence is beyond, greater than IC. IC is the angle of critical angle of incidence. Now my angle of incidence has gone beyond IC, means IT is greater than IC. If that happens, then the angle of refraction will also be greater than 90. means previously it was on the surface, now greater than 90 means it will come back into the medium. So 90 degree greater than 90 means obtuse angle. Obtuse angle means it will come back into the medium. And that is when we say there is total internal reflection. So none of the ray has gone out. 100% of the ray has reflected back. Okay? That is why it is called total internal reflection. Fine? Now, having understood the entire concept, let's go to the associated phenomena which we see all around us. We will see why stars twinkle. We will see early sunrise and late sunset. Why does it appear so? And then we see finally the rainbow. So these are three things that we will study in this chapter, which are directly associated with refraction of light phenomena. Alright, let's see. For understanding all these phenomena, you have to first understand how is the atmosphere made. You have to understand the atmosphere above the earth. It's very important to understand if you have to understand these principles. So let's see. So now if you see, the earth has got layers around it. So from here till here, there is the atmosphere, which is an envelope around the earth. But that envelope is not uniform. The layer which is nearest to the earth is the most densest. Then you have slightly rarer, then slightly rarer, and then slightly rarer. And finally, it is vacuum in the space. Yeah. So when you analyze the atmosphere, it is not a homogeneous density envelope. It is an envelope around the earth which has got varying density. Right. So it is like you can consider different density layers. So each one will act like a separate medium. Yeah, because densities are different. So they will act like mediums. And the mediums are becoming rarer, more rarer, and the rarest. That's how it's going. What have you studied when you are on the Earth's surface, the air is going to be densest, right? So when the refraction happens, it is going to happen away from the normal. So if the light source is here, although it should have gone straight, it doesn't go straight. Here it will bend like this, then here it will bend like this, and then it will bend like this. So it is actually curving below. It is actually curving below. Clear? So, although really you feel that the star is here, actually the star is here. You see? If it was a denser medium, then you would have seen it here. Correct? Apparent position. Where is actually the star? The star is here. Clear? Same thing happens with the sun. This is the horizon. If a person is standing here, this is the horizon. The straight line on the surface, when you are there, the straight line is the horizon. Below this, it is below the horizon, and when it is above this, it is above the horizon. So when I stand here, when a person is standing here and observing the sun, let's say, actually the sun could be here. In reality, the sun is here, but you are still able to see it. Why? Because even if it is here, below the horizon, due to the refraction, it is able to reach your eyes here at this point. Because it's going to be a curve, it's not going to be straight. Not necessary that the sun has to be here for you to observe it. Even when it is a little below, you are able to observe it. So that is how we say there's early sunrise. Similar thing happens when there is a sunset. So when there is a sunset, when the sun is coming down, actually you should not be seeing the sun below the horizon when it goes below the horizon, but you are able to see it. You are able to see it for some time, a brief time, even when it goes below the horizon, because of refraction, because it will be observed till this position. You can observe the sun till this position. Okay, so that's how we say early sunrise and a later sunset we are able to see from the actual. Right? Now let's go to the last part, which is how does a rainbow get formed? Supposing we take this as a drop of rainwater. There is sunlight, which is white light, which is incident on the droplet of rain, and once it crosses from the air to water, meaning it is traveling from a rarer medium to a denser medium, it will bend. So for example, the red light will bend lesser, violet bends the most. So we are taking the two extremes. We are taking the one which is the least bending and one which is the highest bending. So every other ray is going to be in between them. So you have got indigo, blue, green in between this patch, between this space. Alright? Fine. Now they are incident. Most of the light will pass on. However, here they do not pass on. There is total internal reflection. When does total internal reflection happen? When the angle of incidence is greater than the critical angle. Is that clear? So here the angle of incidence goes beyond, greater than the critical angle of incidence, and that's how total internal reflection happens. Nothing goes outside. Total internal reflection happens, and then again there is a refraction here. So here there is a dispersion at this point. Here that is total internal reflection happening, and here there is refraction happening. So what did you understand? Rainbow comprises of all three phenomena, whereas the dispersion, total internal reflection and refraction. All three phenomena you can see in the formation of a rainbow. Is that clear? And then these seven different colors will be in between this patch, and you are able to see from here. Yeah, so you are able to see. Alright? Now the last part of the chapter, the numericals. For numericals, you need to remember three formulas, and those three formulas are going to be: one, the Snell's law, of course, that is sin I upon sin R is equal to a constant. That constant is called refractive index, nu. Here, how to read this? This is read as refractive index of medium 1 with respect to medium 2. I repeat, how do you read this? Refractive index of medium 1 with respect to medium 2. And what is the formula? The formula is V2 upon V1. What is V2? Velocity of light in the medium 2. And what is V1? Velocity of light in the medium 1. Is this very clear? Very important. Remember that. The third is the reciprocal law. Supposing you don't want refractive index of 1 with respect to 2, but you want refractive index of 2 with respect to 1. If it is 2 with respect to 1, then you simply do reciprocal of this. So reciprocal is also acceptable here. refractive index of 1 with respect to 2 is nothing but reciprocal of refractive index of 2 with respect to 1. So these are three formulas which you can use in the problems that can be asked. Just find out which formula is applicable to which sum and you will be able to do it. I wish you all the best for your exams. Bye.